Bonjour, and welcome back to another episode of T.E.D Mini, where together we'll be learning about technology, engineering, and design. In today's episode, we'll be exploring 4 new basic components. This video is a continuation on the other video called Basic Components. In today's episode, we'll be exploring 4 new basic electronic components and their most common basic application in school. Let's start with our first basic component, the diode. A diode is a cylindrical shaped component which has a positive and a negative side called an anode and a cathode respectively. To identify the cathode, a silver band is printed next to the terminal. The use of the diode is to control the direction of current flow. Current passing through a diode can only pass in one direction, which is aptly called the forward direction. Current trying to flow in the reverse direction is blocked completely. One of the most common uses of diodes is in bridge rectifiers. Bridge rectifiers are simple circuits which make use of 4 diodes to convert alternating current into direct current. Think of it this way. An alternating current is like waves in the sea. Imagine the AC voltage to be 10 volts. This simply means that the waves are going up to 10 volts, then dropping down to 0, and then keep going down to minus 10 volts, and returning back up to 0 volts. This type of wave is very common in nature and is called a sinusoidal wave. To convert this into direct current, let's follow its path through the bridge rectifier. Let's imagine that we are in the section of the wave which is a positive voltage and the flow of current is from the top. As the current travels, it is faced by 2 paths, D4 and D1. Diode D4 is blocking the path, so the only way for the current to pass is through D1, traveling through the bulb and back to the new paths called D4 and D2. Although the current can now pass through both, if the current passes through D4, it will come across itself. However, if it had to pass through a diode D2, it would find the quickest way back to the negative terminal of the AC supply, so it chooses that path. Now we are in the section of the wave with a negative voltage, so the current is traveling in the opposite direction. So, as it leaves its source, it comes across paths D2 and D3. Diode D2 is blocking the current's path, so it can only pass through diode D3, through the bulb in the same direction as before, and back to paths D4 and D2. Once again, although both paths are available to take, if the current passes through diode D2, it will meet itself. However, if it passes through diode D4, it will find the quickest route back to the terminal of the AC source. As you can see, our output voltage, although still very bumpy, is all on one side of the graph now, meaning that it is always going to be in the same direction, hence becoming a direct current. To smooth out the bumps, we could add a capacitor, but that's for another time. Moving on to another variation of diodes, we have light-emitting diodes, or LEDs for short. LEDs only allow current flow through one direction. However, they have the added advantage of being semiconductors, which means that they let the light emit through them when electricity flows through them. LEDs come in a variety of colors and use very little power. However, it is very important to note that different colored LEDs have different specifications, such as the range of voltage in which they work and the amount of power they consume. Our second components are called voltage regulators. Voltage regulators are small integrated circuits with 3 terminals which are used to control voltage. To be more precise, they maintain a constant voltage output when the electric supply is not very stable. Look at them from front. The left terminal is the input, the middle terminal is the ground, and the right terminal is the output. A commonly found voltage regulator in schools is the L7805 CV model, which can handle up to a maximum DC voltage of 35 volts at its input and produce a stable 5 volts, 1.5 ampere DC output. The only time these relatively hard-wearing components do not produce a stable output is either when the input voltage drops critically low, the amount of current being drawn by the output is over the 1.5 amperes it can take, or the temperature of the voltage regulator becomes too high. Moving on to our third component, we'll now look at operational amplifiers, or op-amps for short. Op-amps are like magnifying glasses, but instead of amplifying texture or text, they amplify voltage. Op-amps are also made from integrated circuits and come packaged as either an 8-pin integrated circuit containing one operational amplifier or much larger ICs with multiple op-amps sharing some common pins. Basically, each amplifier needs 5 basic terminals. 2 terminals are used to input the voltage of a wave and are called the positive Vin and negative Vin terminals. Two terminals are used to connect the op-amp to a strong power source, from where both the power needed for the IC to function are taken, as well as the power needed to produce the output signal with the amplified voltage. These are called the positive V supply terminal and the ground supply terminal. The last terminal is the positive output terminal. This is used together with the negative ground supply terminal to produce the amplified output voltage, or Vout for short. The fourth and last component for this episode will be the transistor. Transistors are generally used as tiny electronic switches or as current amplifiers, but for this episode, we'll focus only on the latter. Transistors come in two versions, NPN and PNP transistors, which in very simple terms describes how the materials which make them work is packaged inside. To keep things simple, you mainly need to know that both transistors have three terminals. The base is the input for the current signal that will be amplified. The amplified current then flows from a power source through the collector and the emitter, providing an amplified current. It is important to note that the transistor needs a minimum of 0.6 volts as its base to trigger, and we normally add a resistor to the base pin to control the amount of current flowing through it. Transistors are very sensitive devices, and thus it is very important the pins are not mixed up. It is also very important to remember that transistors cannot have both a very high amplification or gain as well as a high current flow through their collector. So when we need to connect a higher current component such as a motor, we need to connect a high gain transistor to a high current transistor in an arrangement called the Darlington pair. This arrangement allows the circuit to have both the high gain or amplification as well as the large amount of current to flow through it. And that will be all for today's episode of T.E.D Mini. If you have been, thanks for watching.